Okay, so in this video we are going to go over the long-awaited and hopefully much anticipated conjugate gradient algorithm. There's several ways to come up with the conjugate gradient algorithm. We're just going to see it sort of as a natural consequence of the D-Lanchhaus algorithm that we just looked at. So let me remind you just some basic notation. We're going to change notation slightly in this video, but for now, if we just go back to the notation that we had from the previous video, from the D-Lanchhaus video. Remember that we updated our solution as follows. We had xm, the updated approximation, is equal to xm minus 1 plus some scalar. It was zeta m times some vector Pm. And the Pm is part of this big P matrix. The zeta m was part of this Zm vector, and so on and so forth. You can look back at the D-Lanchhaus video. Hopefully you have seen it recently to sort of get an idea about exactly where these numbers come from, or where these numbers and vectors come from. That is, where this comes from and where that comes from. Okay, so I'm probably going to stop doing the arrows because I don't do that consistently, but it was important for the previous video since there was a bunch of matrices and scalars and vectors all together in the same matrix even. Okay, so there's a couple of things that I want to point out here. The first thing that I want to point out is when we looked in when we first looked at like the FOM method and the Arnoldi algorithm, we saw that the residual R sub n equals B minus AXM. Whoops. That chalk is getting small here. Minus AXM. We saw as a consequence of the Arnoldi algorithm that this is just equal to some constant. I'm going to call it sigma sub n. It doesn't matter what that constant is right now. Sigma sub n times the vector Vm minus 1. There I go again, putting an arrow just kind of randomly. Okay, so then the residual at step m, that is B minus AXM, is in the direction of the m plus 1th Arnoldi vector. Now this applies in the Lanchhaus case too, because the Lanchhaus case, remember, is just a special case of the Arnoldi algorithm. So this is true in the Lanchhaus case as well. So what this means is that since the Vm plus 1 vectors are orthogonal, it means that the residual vectors are orthogonal. Whoops. They are orthogonal. Okay, meaning if we just do the standard inner product, Rj, Rk, this is going to be equal to 0, and this is for j, it's not equal to k. Now the reason I point out standard inner product is because there are going to be other vectors that are orthogonal relative to the A inner product. So now what we want to do is we want to consider the case where not only is A symmetric, but it's also symmetric and positive definite. Now, in the case that A is symmetric and positive definite, all of the geometric interpretations that we looked at a couple of weeks ago are in effect now. So we can define an inner product using the A matrix since it is positive and semi-definite. And so what my claim is, is that the P vectors, my claim is that these are A orthogonal. Okay, so what I mean by that, I mean if we do A, Pj, Pk, that's going to be equal to 0, and again for j not equal to k. Why is that true? Okay, so it's a fairly straightforward computation that I can just sort of do across the line here. So what I need to show then, if PM is a matrix that whose columns are the p vectors. We're going to have PM transpose times A PM. Now what I need to do is I need to show that this is a diagonal matrix. Okay, that's just another way of saying this. It's similar to how if I want to show that something is orthogonal to a subspace, I need to show that if W is a matrix whose columns span that subspace, I need to show W transpose times that matrix is equal to the zero vector. That's what I'm doing here. Okay, APM is like this, and then we're doing PM transpose, which is where we come up with here. So what this is, if you look at the KJ entry here, it's going to be equal to APJPK. So the KJ entry, or JK, because this is going to be symmetric, since A is symmetric, the KJ entry or the JK entry is going to be equal to this quantity right here. And so we need to show this is a diagonal matrix. So in other words, if K is not equal to J, APJPK is equal to 0. Okay, so how can we do this? Well, we're gonna start by recalling what PM is equal to. We define PM to be equal to VM times UN inverse. So we're going to take the transpose, then we're going to have A, and then we're going to have PM again, which is going to be VM times UM transpose. Sorry, not UM transpose, UM inverse. Okay, so now remember what the rules are for transpose. It flips the order. So now we're going to have this being equal to U in minus 1 transpose times VM transpose A, and then VM U in minus 1. Okay, so now what's going to happen here? Well, remember VM transpose AVM, in the case where we're doing full orthogonalization, which is what we're doing here, because in the Lanchhouse algorithm, it's incomplete orthogonalization, but since A is symmetric, it's also full orthogonalization. In any case, this right here is going to be the HM matrix, or as we call it for the Lanchhouse case, the TM matrix, since it's not merely Hessenberg, but it's also tridiagonal. So then what we're going to have is we're going to have our UM minus 1 transpose, and then VM transpose AVM is just equal to TM, and then we multiply by U in minus 1. Okay, but remember what the relationship is between UM and TM. TM is equal to LM times UM. So TM is equal to LM times UM. So when we do TM times UM inverse, we're just left with LM. So this now is going to be equal to UM minus 1 transpose times LM. Now there's a number of ways to see this, and I will let you guys figure out how you want to see this on your own. UM is upper triangular, so its inverse is also going to be upper triangular. Okay, one way, if you think about the standard way to compute an inverse, where you put a matrix here and the identity matrix here, and you row reduce this matrix until this becomes, so you put your matrix here that you want to take the inverse of, and you augment it with the identity matrix, and you do row operations until this part, the left-hand part, has the identity matrix, then the inverse matrix is going to be on the right-hand side. If you think about the row operations that you have to do, since U is upper triangular, the only row operations that you're going to be dealing with are going to affect that upper triangular part. You're going to be moving, like pivoting from the bottom up, basically. And so what that means is that the lower part of the matrix that starts as the identity matrix is going to stay 0, and only the upper triangular part is going to change. Okay. However you want, there's other ways to think through that as well, but since UM is upper triangular, its inverse is upper triangular. And so this UM inverse is an upper triangular matrix. You take its transpose, its lower triangular matrix, and a lower triangular matrix times a lower triangular matrix is equal to a lower triangular matrix. Okay, so now we know this is a lower triangular matrix. But that lower triangular matrix is equal to this matrix right here. Since A is symmetric, this matrix is symmetric, which means this lower triangular matrix is symmetric. But what's the only way for a lower triangular matrix to be symmetric? Well, it's if it's just a diagonal matrix. So this is actually a diagonal matrix. This lower triangular matrix is actually a diagonal matrix. But it's also equal to this, which says this is a diagonal matrix. So since this is a diagonal matrix, it says that the p vectors are A orthogonal to each other, meaning this right here. Okay, so you might want to record the fact that RJ, RK, they are orthogonal, and we have this orthogonality here. Another fact that I want to remind you of, because we are going to be using it, is when we computed Pn, we computed Pn as 1 over. Let me refer to my notes here so I can use the same notation that we had before. We computed this as 1 over U m times Vm minus beta m p m minus 1. Okay, I'm not going to do the arrow. Okay. Now another thing to keep in mind, as I mentioned before over here somewhere, that Vm plus 1 is equal to Rm. So then Vm plus 1 is a multiple of Rm. So then Vm is going to be a multiple of Rm minus 1. So we can write this as 1 over U mm. And then this is going to be, Vm here is going to be something like 1 over sigma m minus 1, Rm minus 1. Whoops. Minus beta m p m minus 1. Now, the important thing here, the thing that I want to conclude that we are going to be using in the upcoming, in the next part of this video, what we can conclude then is that the vector Pm is in the linear combination of Rm minus 1 and Pm minus 1. So Pm is going to be equal to some constant or some scalar I'm going to call C1 times Rm minus 1 plus another scalar that I'm going to call C2 P m minus 1. Okay, so Pm is in the linear span of Rm minus 1 and Pm minus 1. Okay, so maybe write that down as well, because I'm going to have to basically erase everything to get on with what I need to explain here. Okay. All right, so now what we're going to do is we're going to take the fact that we know that the P's are orthogonal and the R's are orthogonal. We know that we can update from xm to xm plus 1 by just doing xm plus a multiple of these PJs, and we want to somehow be able to use that to come up with another version of the Lanczos algorithm, or find another way to derive the Lanczos algorithm without going through everything that we did before, which involved this progressive LU factorization of the Hessenberg matrix and all of these sorts of things. So we're going to start with the fact that we know that we can implement the Lanczos algorithm in such a way so that the updates are going to be, xm plus, a linear multiple of the p's, and we're going to try to come up with an algorithm that works that way. So here's what we're going to do. So what we're going to have to do is it's not going to be, we're going to have to enforce that the PJs are A orthogonal to each other, and we're going to have to enforce that the RJs are orthogonal to each other. So what we're going to start off with is we're going to say that xj plus 1, so for this algorithm, xj plus 1, we know from the D-Lanchhaus algorithm we can write this as xj. Okay, now there's going to be a change here, xj plus alpha j pj plus alpha j times pj. Okay, so notice the change. Before, and this is the change in notation that I mentioned at the beginning of the video. Before this algorithm, like in this formula here, pj, like the index there, would be the same as the index there. But for the algorithm that we're deriving now, the conjugate gradient algorithm, it's more convenient to have it written this way. So that's going to change just a little bit, and I'll mention some things when we get there. Anyways, so we're going to have this, and the pj's are going to be orthogonal to each other. So we know that we can do this. So we know that such a sequence of vectors exists because we constructed them with the D-Lanchhaus algorithm. All right, so we're going to have this, and then we're going to define the residuals. The residuals are going to be r j plus 1 is equal to b minus ax j plus 1. And similar to what we've done before, we're going to get sort of like a recursive relationship for these residuals, because we can write this using this formula for xj plus 1. We can write this as b minus axj minus a times alpha j pj. Well, this is simply rj minus a times alpha j pj. Okay. Now, if the rj's are orthogonal to each other, I can do the inner product of rj plus 1 with rj. So 0 is going to be the inner product of rj plus 1 with rj. Okay, well, this is one way to write rj plus 1. rj plus 1 is equal to rj minus a alpha j pj and then rj. Okay, and now we can solve this for alpha j. We can solve this for alpha j. And if we solve this for alpha j, we're going to get the following. This is equal to xj plus alpha j. If we solve this for alpha j, it's going to be rj, the inner product of rj with itself, divided by apj rj. And then times pj. Okay. I think I can get one more letter out of my little chalk here. Even more. Okay. And again, if you solve this for alpha j, this is exactly what you're going to get. So this right here is equal to alpha j, and we got it from this relationship down here. And the fact that we are enforcing that the RJs are orthogonal. And we know they can be orthogonal since we just saw that in the D-Lanchhaus algorithm. Okay. So what we want to say now is the PJ vectors. What about the PJ vectors? Well, the pj plus 1, if I want to look at pj plus 1, because we are, because our indices are a little bit different than in the D-Lanchow's version, so in the D-Lanchow's version, we have the following. In the D-Lanchow's version, as I just wrote on the board, we saw that Pm is going to be in the linear combination of Vm, so that's R m minus 1, and P m minus 1. The thing that we need to change, though, is in the context of the conjugate gradient, this Pm is a vector that brings us from xm, in the D-Lanchow's case, the Pm brings us from the xm minus 1 to the xm vector. From the m minus 1 approximation to the m approximation. But in the context of the conjugate gradient, Pm brings us from the mth approximation to the m plus 1th approximation. So to make this, to sort of convert the D-Lanchow's indices to the conjugate gradient indices, I need to write this as P minus 1. Because P minus 1 is what would take us from the xm minus 1 to m. And so this is going to be P minus 2. So if I apply this in the case where m minus 1 is, say, let's equal to j plus 1. I think that's going to be the convenient thing to use. M minus 1 is equal to j plus 1. Then what we see is we see that P j plus 1 is going to be in the linear combination, or sorry, is going to be in the linear span of rj plus 1 plus pj like this. Okay. So that's going to be an important thing for us to note. Okay, so if we convert the D-Lanchow's index statement to the index convention that we use for conjugate gradient, we see that pj plus 1 is in the linear combination of rj plus 1 and pj. Okay. Notice that it's only the p indices that we change. Okay. So, all right. So now what we can say is we can say that pj plus 1 so p j plus, okay, I think, well, no, I still got a little bit more. Well, pj plus 1, as I just mentioned, is in the linear span of rj plus 1 and pj. Now, the magnitude of pj plus of the pj's is not the important thing. The important thing is that they are orthogonal to each other. We can always deal with their exact magnitude in other ways. And we'll see we'll be dividing by their magnitudes, stuff like that. So pj plus 1 is going to be equal to rj plus 1 plus some constant, okay, that chalk is done, plus some number beta j times pj. Now, I want to point something out. The alpha j's and the beta j's are not the same as the alpha j's and the beta j's from the TM matrix from the D-Lanchow's video. We're just reusing these letters. Okay, so pj plus 1 is equal to rj plus 1 plus beta j pj. So now, what this tells us, since the pj plus 1s, since the pj's are orthogonal to each other, if I do the the A inner product of Pj plus 1 and Pj in the A inner product. Remember what this means. I'm going to do the inner product of Pj plus 1 and let's see, Rj plus 1. In the A inner product, what this is going to give us is the following. By definition, it's going to be A Pj plus 1. It's going to be A Pj plus 1 plus Rj plus 1. But Rj plus 1 is Pj plus 1 minus beta j Pj. Actually, you know what? I'm going to write this a little bit different. Okay. So this is going to be Pj plus 1. And then Rj plus 1 is Pj plus 1 minus beta j Pj. And this is in the A inner product. Now, again, the Pj's are orthogonal to us, are orthogonal to each other in the A inner product, which means Pj plus 1, doing the inner product of that with beta j Pj is going to be equal to 0 in the A inner product. And so what we're left with is simply Pj plus 1 Pj plus 1 in the A inner product, A here, or by definition this is just A Pj plus 1 Pj plus 1. Okay, but notice what is this if we compute this in the A? If we compute this, what is the definition of this? Well, it's going to be A, the inner product of A Pj plus 1 and R J plus 1. So notice if we can compare this, if we compare this with this says A Pj plus 1 Rj plus 1. So if the indices here are the same, we just get A Pj plus 1 Pj plus 1. So another way to write alpha j then, we can write this as xj plus rj in the numerator, and in the denominator a pj rj we can write simply as a pj, and then we multiply by pj. Okay, so again, this right here is another way that we can write alpha j. Okay, so I'm going to erase, actually I'm going to keep this and erase this. So I want to use now the fact that Pj plus 1 and Pj are orthogonal in the A inner product to conclude, to deduce the following. 0 is equal to Pj plus 1 in the A inner product. Okay, but what is Pj plus 1? I have this formula here for Pj plus 1. So I'm going to have Pj and then R j plus 1 plus beta j Pj in the A inner product. And again, this is equal to 0. So notice what I can do here. I can solve this for beta j. And I'm going to get that beta j is going to be equal to minus Pj Rj plus 1 in the A inner product divided by PJ in the A inner product. And then if I just want to compute this in the standard Euclidean inner product, it's going to be minus A PJ R J plus 1 divided by A PJ PJ. Okay, so this beta j here is given by this formula here. So now I can write this as R j plus 1 plus beta j, which is given by this formula here, A PJ RJ plus 1 over A PJ PJ and then PJ. Okay. Okay, so the idea here is that we need an iterative algorithm, and basically the stuff in step j plus 1 needs to be defined in terms of the previous stuff. And that's exactly what we're working towards here. Okay. Now, what can we do? What can we do about APJ? What can we do about these APJs here? Well, if I come over here and I look at this formula, come down here and I look at this formula for APJ. So I've got RJ minus 1, sorry, RJ plus 1. If I just bring this down, RJ plus 1 is equal to RJ minus A alpha J PJ. I can solve this for APJ and get that A PJ, okay, if I move this over, I'm going to have, well, sorry, let's think about it this way. Okay. If I do RJ plus 1 minus RJ and divide by alpha J, we're going to get that APJ is equal to minus 1 over alpha J times RJ plus 1 minus RJ, like that. So that's what APJ is equal to. But I know what alpha J is. I can write alpha J in this way right here. So what this means, when I plug this in for beta J and do the algebra, it's just simple algebra to reduce everything to what it needs to be. Beta J then is going to be equal to RJ plus 1 RJ plus 1 over, RJ plus 1, RJ plus 1 over RJ, RJ. Okay. So, all right, so what this does, maybe write down all of these things here, and this gives us the ingredients for the conjugate gradient algorithm. Okay, so this is going to be the conjugate gradient algorithm. Whoops. And here, A needs to be symmetric, positive, definite it needs to be symmetric, positive, definite for this to work. Otherwise, if it's not symmetric, the D-Landshaus thing doesn't work. If it's not positive, definite, using this inner product stuff is not going to work. All right, so step 1, we're going to initialize things. We're going to say R naught is equal to B minus ax naught, and P0 is equal to R0. Whoops. P0 is equal to R0. Okay, step 2. We're gonna have a loop here. This is the outer loop for j equals 0, 1 until convergence. That is until like the relative residual is what we need it to be, whatever we set, within whatever tolerance we set. Sorry, that's 3, not 2. Okay, so now we're going to say alpha j. Alpha j is equal to rj divided by apj pj. This is our alpha j. Remember, rj over apj pj. Wow. Okay. Okay. 4. We're going to say xj plus 1. Xj plus 1 is going to equal to xj plus alpha j pj. So we computed pj. Remember, we computed pj in the previous step. We're going to compute pj plus 1 in this step. So rj plus 1, the residual, rj plus 1 is going to be equal to rj minus, I had it written here before, but it's rj minus alpha j a pj, like this. Item 6 is we are going to get our new beta j based on this formula right here. We just computed rj plus 1, so we can use this to find beta j. Beta j is going to be equal to rj plus 1, rj plus 1 over rj. And then finally, we can now update our pj plus 1 based on this formula right here. So pj plus 1 is going to be equal to rj plus 1 plus beta j pj. Like this. Then 8 is we're done. Okay. Now at some point in this loop here, we're going to have to determine what the residual is here, and we'll talk about that in the lab. We're going to have to determine what this residual is here. If it is within the tolerance that we have set, then we're going to exit. If it's not in the tolerance, then we're going to keep going. But notice what's going on here. Notice how we're just doing, a very few computations in each iteration of this loop. We're not having to store in memory, all of the previous vectors before. So all of the problems that we discussed that FOM, IOM, DIOM have, this does not have that. So this is a very nice algorithm. Of course, the matrix has to be symmetric and positive definite, which is also kind of a big restriction. A lot of the matrices that we've seen in this class for PDEs and stuff do not satisfy that. So for this to work, A needs to be symmetric and positive definite. In fact, this method works so well. One thing that people do when they don't have a symmetric positive definite matrix, they try to do things to make it a symmetric, to approximate a non-symmetric positive definite matrix with an SPT matrix. Okay, so this is the last lecture video for this week. In the other videos, I'm going to be implementing this. It's going to be lab videos, and I'm going to show you how we can implement some of these things in Python.